So then let's start the seminar. Good afternoon and hello to everybody. Thank you for joining our today's seminar entitled Machine Learning in Heliophysics, Trailblazers in Graz. So today we will hear about recent applications of machine learning in heliophysics. We have three additional speakers here. We welcome Hannah Rüdisser. She is a master student at the Know Center here in Graz, and she works on the automated detection of interplanetary coronal mass ejections in solar wind data. Then we have Martin Reiss. He's a postdoc here at the Institute, and he will talk about the BZ prediction in such interplanetary coronal mass ejections. And then we also welcome Rachel Bailey. She's a postdoc at the Zentralanstalt für Meteorologie und Geodynamik, ZAMG, and she will present her work on the prediction of geomagnetically induced currents. But before Hannah, Martin, and Rachel delve into their work, let me briefly introduce to you an Horizon 2020 project, which is called Europlanet 2024 Research Infrastructure and its machine learning activities. So Europlanet actually has already a long-standing tradition in Europe. It has been funded by the EU for, let me think, for more than 15 years, definitely. The current Europlanet project is led by the University of Kent, and there are about 60 beneficiary institutions all across Europe and nearly as many affiliated partners all across the world. And the project is called a research infrastructure because it provides access to different facilities, services, and tools, as there are, for example, access to laboratories or geologic field sites across Europe, but also in other parts of the world. It also provides virtual access to different services, as for example, a geologic mapping tool for mapping planetary surfaces. And it grants also access to telescopes for observation time, for example. There are also different networking activities aiming at strengthening the planetary science community in Europe. And one of the new activities in this current Europlanet project is the work package number 10, which is called Machine Learning Solutions and Analysis and Exploitation in Planetary Science. This is led by the Space Research Institute, and actually it's coordinated and managed by myself. My deputy is Andreas Windisch from the Know Center. So in our work package, we have, or sadly I have to say, we had 9 beneficiaries because due to the unfortunate war of Russia against the Ukraine, we had to suspend our Russian colleagues from the project. So we now have 8 beneficiaries. Those are not only science institutes. I can imagine you recognize some of those institutes, but we also have institutes that are dealing more with business and industry machine learning applications. But that's exactly one key point of our work package, because we want to integrate those machine learning expert knowledge into the planetary science community, because there are completely different challenges when you work with spacecraft data than when you work with business or industry data. So in our work package, we develop data analysis tools that are optimized for planetary science, and we want to promote and foster the use of machine learning and data-driven space research. And also we want to show what machine learning is capable of. We also want to ignite a further discussion about more applications of machine learning in different areas of science. As I said, we develop data analysis tools. We call them machine learning pipelines in our work package, and they are completely open source. They are freely accessible, and everybody can use them, modify them. So this is also one key point here in Europlanet, that all of the tools and services we develop are freely available to everyone. So what are now those planetary science research questions that we tackle with machine learning technologies? So we have here a couple of so-called science cases that were proposed by the science institutes that are now the beneficiaries of our work package. For example, we have here the automatic detection and classification of plasma boundary crossings, as there are bow shocks or magnetopods around Mercury or around Earth. For example, in the Mercury case, our machine learning pipeline is, so to say, finished, and we're right now in the progress of writing a paper about that. Then, as I briefly mentioned, Hannah will talk about her work in our work package, which is about the automatic detection and classification of ICMEs in solar wind data. Here, the paper is ready to be submitted. Then we have also a science case about the classification of the surface composition on Mercury, or to identify minerals in reflectance spectra. And also we have a machine learning pipeline for the automatic recognition of planetary surface features on Mars, as there are, for example, mounds or pits. And for the mounds case, we also are right now writing a paper. We also have want to develop a pipeline for the detection and classification of meteors or asteroids. And we are right now working on the science case to classify plasma wave emissions in electromagnetic spectra. So now, you know that we are working, we're trying to develop machine learning pipelines or data analysis tools for all of those science cases, but how can you get now more details, or how can you get hold of those tools, of those pipelines? So for this, we set up a so-called machine learning portal. This is somehow the main access point to our activity, our machine learning activity within Europlanet. You can find it in the address here, given at the top of the slide. And as you can see, you will find here more details, information, introduction to all of the science cases. You find tutorials for our science cases or for other machine learning problems. You find announcements for our workshops or the workshops material there. The presentations we gave in the past at different conferences or other opportunities, also announcements for sessions dedicated to machine learning. So feel free to hop by and click through our portal. And we also have, of course, a GitHub account or a GitHub organization. This is completely public. All of the machine learning pipelines tools we develop are there. We put there. You can download the code, for example, for the ICME science case. Hannah also provided a tutorial for that. And we also have the pipeline there for the Mercury, boundaries around Mercury, or also from our workshop where we introduced this pipeline, and also here for the surface classification pipeline. So if you feel that one of our pipelines could assist you in your research, or you're just interested, please feel free to download them, use them. If there are problems, file issues, or if you have any other questions, contact me. Here as a reminder is my email address. So we would be happy if our pipelines, our codes, our data analysis tools are of use for anyone else. So with this, I want to thank you for your attention, and I leave the stage for Hannah.
All right, thank you for the introduction, Ute. I'm quickly going to share my screen. All right, can you all see that?
Yes.
Okay.
Thank you.
Thanks again for the introduction. My name is Hannah Rüdisser, and I'm going to talk to you about the automatic detection of interplanetary coronal mass ejections in solar wind in situ data. As already mentioned, the project is part of the Europlanet 2024, and I'm currently doing my master thesis on it at the Know Center in cooperation with the IWF. So today I want to quickly guide you through our work, what we've done so far, and what there still is to be done. I'm going to start doing this by quickly presenting a recap on what are ICMEs, what are the features of an ICME, how are they catalogized, and what may be the difficulties when trying to detect these events. Afterwards, I'm going to talk to you about the machine learning part, more specifically about convolutional neural networks, how they are applied in medical image segmentation, and finally, how this relates to our pipeline. And finally, I'm going to talk to you about the results of our work and provide a quick outlook, what problems we experienced, and what the next steps will be. Okay, so I'm going to start by quickly reminding you about ICMEs in solar wind in situ data. So in general, we have spacecraft who are constantly measuring the solar wind. And even though most of the time no events happen, sometimes it is disturbed by a so-called ICME. And these ICMEs can be seen in the in situ data, which is collected by these spacecraft. Here we have a picture of an example. And usually, or let's say sometimes, these events start with a shock and then with a sheath. And then we have a magnetic cloud, a smooth rotation of the magnetic field, and an enhanced total magnetic field. For this example here, we have a first enhanced and then a monotonically declining speed profile. We have a proton density decrease after the increase during the shock and the sheath here, and we have reduced proton temperature. I'm saying for this example because a big problem is that not all events exhibit all these signatures. There are signatures that are only present in some ICMEs. There are signatures that are present in most ICMEs, but there's not one single feature that takes place in all of them. All right, so now that we were reminded about ICMEs in general, there are various spacecraft collecting in situ data where we can take a closer look at and possibly find ICMEs. For example, WIND Stereo A or Stereo B. And taking a closer look at the WIND spacecraft, there are many different catalogs. We've only listed 4 of them here. And on the right, you can see a picture showing the number of events per year in a specific catalog. And as you already can see, there are events, or there are a lot of events where experts do not agree always. So depending on how loose or how strict you set the criteria for an event, you either have more or less ICMEs. So the experts already disagree, and thinking about that, there are already a lot of spacecraft collecting this data, and there will be in future missions. This calls for an automatic detection, because otherwise just using human expert labeling would be very time consuming. Okay, I've already mentioned some of the difficulties that come along with the automatic detection. One of them is, as already mentioned, that not all events exhibit standard signatures. And one more problem is that we have a high variability in duration, as we can see in the picture here. Some only last a couple hours. Some of them last up until 80 or even more hours. And even though most of them last around 20 hours, this is quite a high variability. As already mentioned and discussed before, even experts sometimes disagree about an event being an event or being not an event. And this is not the only thing that is disagreed about. The start and the end time are also very vague. So there's not a strict criteria saying, okay, this is where the event starts, this is where the event ends. So we have another thing that experts sometimes disagree about. And what is more, on top of all of these problems, ICME events are rare. Most of the time, nothing happens. And we have not that many events, as we could see during the plot before. Okay, so far I've told you about ICMEs in general, about the problems that come along with detecting them. And now I want to go on with the machine learning part. However, I want to mention that if you're really interested in the machine learning part, this will probably not be enough time to really give you all the details, but I want to give a quick overview. Okay. I think there was a seminar about general machine learning a couple of weeks ago, and I want to quickly remind you about convolutional neural networks and how they work. So neural networks in general, they're inspired by the human brain. And the convolutional neural networks are commonly used for computer vision and image recognition. So they're inspired by the visual cortex. They detect patterns in data which is arranged in grids. So for example, images. And as we can see here in the picture on the right, on the upper right, here we have a car, then we have a network. And in the end, we want our network to classify, is it a car, is it a truck, what kind of vehicle is it? Just looking at the picture as a human being, we can obviously see that it is a car, but thinking about what exactly makes us decide, okay, it is a car. It's not the overall picture, but it's small features such as the tires or the headlights. And these features need to be learned by our network. So we have the feature learning part here, and we have the classification part here. Down here, we can see the feature learning part and how that is conducted for for facial recognition. In the beginning, so in the more shallow layers, we usually learn very simple, very low-level features such as edges, may they be horizontal or vertical. And these simple features are then used to construct more complex features, eventually leading to features that make us decide, okay, what type of face or what type of vehicle is that? Okay. So convolutional neural networks are often applied to medical image segmentation. And even though you may ask yourself, why is that important? Stick with me for a second. Here we can see medical images showing polyps. And the task here was to segment those images into parts that are a polyp and parts that are not a polyp. A very recent advance did very well on these types of tasks, namely the UNet architecture. I'm not going to go into much detail, but in general, our network is not aligned one after the other in a straight line, but it's bent like a U. And it has the advantage that it's very good at first realizing what is present in a picture, second, where is it present. So this led to very good results in the area of medical image segmentation. And even though it's not straightforward to apply that to our specific task, it definitely works, because thinking about how our computer sees pictures, it does not just see the picture as we do, but it sees pixels with values. So for the computer, a time series is not that different from a normal picture. That's also why what we did is we took our time series and segmented it in a way similar to the polyp detection, meaning that here we have the ground truth, the label, and we segment our time series into areas where there is no ICME present and areas where there is an ICME happening. We did use a variation of a ResUnit++, which was proposed in 2019. I'm not going to go into too much detail because it's quite complicated. But if you are interested, as Ute already mentioned, we have code and tutorial available on GitHub, and you can take a closer look at it, even though the most recent code still has to be uploaded within the next days. But you can still get a general idea already. Okay, now that we know how convolutional neural networks are applied to our problem, I'm going to take you through the results that we achieved and provide a quick outlook on what's next to come. In general, we tried out our pipeline on wind data, stereo A data, and stereo B data. But since the time is limited today, I'm going to show you only the results for wind data. And here on the left, we can see the same picture that we saw before, but now we have the results of our pipeline in the bottom panel. So as we can already see, it manages to get a general idea about what is an ICME. Of course, it doesn't match them perfectly. It doesn't match all of them, but it definitely gets, let's say, most of them. To specify that even more, let's take a look at the figure on the right. So in general, we tested the pipeline on wind data between 1998 and 2015. And within that time, we had a total of 640 ICMEs. Within that time, our pipeline detected 720 ICMEs. And these two numbers are divided in true positives. A true positive is an ICME that was detected by our pipeline and was also part of the catalog. Then we have false negatives, 174. These are events that were listed in the catalog but could not be detected by our pipeline. And then we also have the false positives. We had 200 and 54 false positives, meaning events that were detected by our pipeline, but were not in fact ICMEs listed in the catalog. All right. Another thing I want to mention is that, of course, detecting an ICME does not mean 100% overlap all the time. Sometimes our pipeline manages to find start and end time very well, but sometimes, as in the upper right image here, we match only the end time quite well, but the beginning is not quite clear. Or for the lower left image, we have the beginning, which is clearly met, and the ending, which is not so well matched. We took a closer look at the mean absolute error of the start time and the end time, and we found a mean absolute error of 2 hours and 56 minutes for the start time, and a deviation of 3 hours and 20 minutes on the end time. Thinking about that, we possibly want to use this pipeline on early warning system. This is already quite good. It's not perfect, but it's okay. All right. So as I already mentioned in the beginning, experts do disagree often. And since we're using supervised learning, we have bias in our labels, and these biases are included and learned when we train our network. Meaning that if the ground truth isn't perfect, our pipeline probably will not be perfect either. Something I just wanted to show you is here on the left, we have an example of a false negative, meaning this was an event which is part of the catalog that our pipeline did not manage to find. And here on the right, we have a false positive. This is an event that our pipeline found, but it was not part of a catalog. And as you can already see, not being an expert, these definitely look similar. And so this basically leads me to our main result. We cannot expect our pipeline to perform perfectly just because the label is very unclear, and human experts already have problems to detect, is this an ICME, is it not? And of course, this uncertainty also applies to using a machine learning pipeline. However, we're quite pleased with the results. And so the outlook, or the next steps that we'll take, will be we want to combine this tool with other forecasting tools. For example, the ones that will be presented later on by my colleagues. We could also apply our time series event detection to other problems that are similar to that. As already mentioned, there are many more problems that are similar within the Europlanet, or maybe you too have problems that this might be applicable to. Thinking about the amount of data which will possibly exist in the future, we could use the pipeline to label data in future missions. And as Ute already mentioned, we're happy that the paper will soon be submitted for publication, and this already quite in its final stage. Okay, so that was a very brief overview of our work, and I hope I got you an overall idea of what we're doing. If you have questions, I'm more than happy to answer them. And if there are questions that we will not be managing today, you can always contact me. Here's my email address, and I'm always happy to talk about our work. So thank you for your attention, and I'll give back to Ute.
Okay, thank you, Hannah. So there are questions in the chat, but as mentioned at the beginning of the seminar, we will collect them and then have a discussion later on after all the presentations. So now, Martin, would you please start your presentation? Thank you.
So I hope you can see my screen and hear me okay. Good afternoon, everyone. My name is Martin Reiss. I'm currently a postdoc at the Space Research Institute in Graz. And as you know, at any point in time, our solar system is basically filled with tens or even hundreds corner mass ejections. So these ICMEs, Hannah was already talking about, are magnetized clouds of plasma that are expelled from the solar surface in the most extreme explosions in our solar system. But still, we don't really understand how geoeffective an ICME will be when hitting Earth's magnetosphere. And so our study really tried to answer the question if machine learning can solve this so-called PZ problem. So a little bit more specifically, the research question that we studied was if upstream in situ measurements, so information of the sheaf region of an ICME, plus several hours of the magnetic obstacle, are basically sufficient to predict estimates of the PZ component. So estimates of the magnetic configuration inside the ICME. And the tool we are using the tool we are using to test this question is based on machine learning. And what is illustrated here on the left side on the slide is the main concept that we applied. So we used properties, so physical properties from the sheaf region of the ICME as an input to machine learning in order to predict the minimum value of the PZ component in the magnetic obstacle, shown here as a blue line. And after this presentation, after this short introduction, I hope that I was able to really explain how this tool works and also how it performs when we apply it to real-world data. So my talk is structured in the following manner. First, I would like to talk a little bit about the why. So why it is actually important to have an accurate picture of the PZ component inside ICMEs. What's the research question and how does our tool work? Then I would also like to talk a little bit about the results and also about the lessons we learned and some future plans and future objectives. So why does it actually matter? So why is an accurate picture of the PZ component inside ICMEs important? So we know that the PZ component of the interplanetary magnetic field largely determines the amount of energy and momentum that is transferred from the solar wind into Earth's magnetosphere. But currently there's a lack of forecasting capabilities, and the community usually refers to that as the PZ problem. And quite ironically, during ICMEs, when accurate PZ estimates are basically needed the most, the PZ problem is most relevant and most difficult. And solving this PZ problem is really challenging for a number of different reasons, mainly because of observational reasons, because we don't understand what is happening in the early evolution of an ICME. We don't really know what is happening in interplanetary space, how the ICME interacts with ambient solar wind, and so on. So a number of problems make solving this problem very challenging. And without a definitive physical solution, one promising approach that we can take is to develop new predictive tools. And these tools already exist, and they are usually based on empirical relationships, on statistical extrapolation, pattern recognition, and more. However, thus far, the community has really paid little attention to using upstream in situ information in order to predict the PZ component in the magnetic obstacle of an ICME. And here we present probably the first tool that tries to do exactly that. I also would like to mention right at the beginning that we really reduce the complexity of this problem at hand by focusing just on the minimum value of the PZ instead of focusing really on the temporal evolution of the PZ component in the ICME. So just to summarize quickly again, here you see an overview of the research question we addressed and the tool we used to solve that. So the question we try to answer is can we use upstream in situ information in order to predict the PZ component in ICMEs? And the tool we developed consists of three main components, namely data input, the feature extraction, and the machine learning algorithms. And I would like to go a little bit into detail with all these 3 points. So first, I would like to talk a little bit about the data. of course, in order to train a model, we need enough data. And here we use this ICME catalog that is collected and maintained by Christian Möstl from the IWF Graz. On the left, we see the arrival times of the magnetic obstacles of an ICME in this catalog. In red, we see stereo A, and in blue, we see stereo B, and in green, we see wind data. And this just gives you an impression of the location where we collected the data that we use then to train our models. And just the main headlines for the data part, all the ICMEs that we are using were observed from between the years 2007 to 2021. All the events were measured by the wind, stereo A and stereo B spacecraft, close to a distance of 1 AU. And I also would like to emphasize that our selection only includes 348 ICMEs that all of them showed a very clear magnetic obstacle signature. I would also like to go a little bit into detail about this tool, about the machine learning approach that we applied. Of course, we need to specify the data input, specifically the features and the targets. So we study the physical properties of all these ICME events in the catalog, including the magnetic field, including the speed, density, and temperature. And we also look into combinations of these different properties. And as the target, what we want to get out of the machine learning model, we focus here, as I said already, on the minimum value of the BZ component, and also on the maximum value of the total magnetic field as a kind of a proxy as how bad it can get for the most severe BZ disturbances. And for each of these 7 physical properties, we calculate 6 different statistical measures. So these measures include basic statistics like the mean, the standard deviation, the minimum and maximum values, the ratio between the maximum and minimum values, and also the ratio, for example, between the mean value and the standard deviation. And this process results in 6 times 7 features, so 42 features, which we calculate for the whole ICME catalog. And then we try to use these features as input to machine learning in order to predict those 2 targets that we defined. Regarding the machine learning algorithms itself, we use a simple linear regressor as a kind of a baseline model to see how a simple model compares to our more advanced techniques. We also investigate a random forest regressor and the gradient boosting regressor, all of which from the Python package scikit-learn in order to train our model. Regarding training and testing, what we did was that we split from the beginning the whole ICME catalog into 70% training and 30% testing, where this test set is not further used in the training process, it's just used then for the final validation. And during the training, during the process of training, we use a 5-fold cross-validation and also apply early stopping, which means that the model training is basically stopped some steps before it reaches the minimum in the loss function to prevent overfitting. And what are the results? I just want to give you a few glimpses of the results and the metrics that we calculated. In total, we calculated 15 different metrics and really conducted a very comprehensive validation analysis of this tool. I just want to give you the easiest representation that we can think of, which is just the comparison between the observation on the x-axis and the prediction on the y-axis. On the left, you see the results for the minimum PZ predictions. In the middle, you see the results for the maximum PT predictions. And on the right, I also summarized some error measures that we calculated. For example, the root mean squared error, and we see that the root mean squared error, for example, just to give you a feeling for the numbers, for the random forest regressor, for the mean PZ was, for example, 4.73, and we got a correlation coefficient of 0.7. And for the maximum PT, we got a root mean squared error of 3.79. nanotesla and a correlation coefficient of 0.88. And I also would like to mention that we had a summer intern who, in addition, tried to test the neural network in comparison. And we found for this neural network that the student developed a root mean squared error of around 5 nanotesla. I also would like to mention that the full source code and the full ICME catalog is available online in our GitHub repository. So if you're interested, please check out the links I'm providing then on the last slide. Everything is open source. You can also play around a little bit with the Jupyter notebook if you're interested. And yeah. I also would like to talk a little bit about the lessons learned from this study. Sort of probably the most important lesson that we learned was that focusing on the minimum value of the BZ and also on the maximum PT is much easier than really predicting this temporal evolution. But still, it's quite important from the perspective of an actionable forecast. But this step definitely significantly reduced the complexity of the problem. One open question we were not able to answer is how well can we extrapolate the predictive skill that we observe here in this experimental setting? How well can we transform that to an operational forecast? So we clearly only focused on a subset of ICMEs, so only ICMEs that really show the clear magnetic obstacle signature. But we know, of course, there are a lot of different phenomena, as Hannah also mentioned, that show similar characteristics, and it's very difficult to differentiate them for the different ICME types. We also know that any operational application of this tool, I'm talking about any application of such a tool, we need an accurate automated ICME detection. So exactly the tool Hannah described. We also started first collaboration to combine our tools, and the first results look quite promising. But combining such a predictive tool for the BZ prediction with an automated ICME detection algorithm also introduces a lot of new challenges. For example, like how can we get rid of timing errors, and how does this timing error, for example, of an ICME start, how does this, for example, affect the accuracy of our tool? And there are a lot of challenges that we have to tackle in order to really combine that and make that happen and really apply that in operations. I also would like to talk a little bit about future perspectives. So one of the future perspectives is the implementation, the test of this detection tool, coupled then with an automated ICME detection tool. We also would like to work on new strategies on really not only having this estimate of the minimum value, but also really look into the temporal evolution of this set. So one promising avenue might be using the semi-empirical flux rope model that was developed by Andreas Reiss at the IWF Graz. So the idea would be to fit the rest of the magnetic flux rope from the first few hours of the ICME. So one advantage of the model by Andreas is that it's super fast and you can produce a large ensemble of solutions. And so the idea would be that if we see the first few hours, this could help us then to narrow down the number of possible ensemble solutions that can give us then really the temporal evolution of the magnetic obstacle. So to conclude this talk, I would like to just summarize a little bit the headlines. So the key points, we studied the question if upstream in situ measurements are sufficient for predicting the BZ component in ICMEs. We select machine learning as a tool to study this question on the example of 348 ICMEs. We found quite reasonable results, with mean absolute error of 3.12 nanotesla for the mean BZ, and the mean absolute error of 2.23 nanotesla for the max BZ. But to answer my original question, if machine learning is able to solve the BZ problem, I think that this tool is far from solving the BZ problem, but we find that this prototype really shows some first promising results, especially for ICMEs that have a clear magnetic obstacle structure. So again, if you're interested in this study, I've also put some links here that you can visit. I would also like to acknowledge funding from the FWF project Enhanced Lead Time for Geomagnetic Storms, led by Christian Möstl. If you have any questions, please feel free to contact me or Christian. Thank you very much for your attention.
Thank you, Martin. And now let's immediately switch to Rachel, please. Martin, I think you have to stop your screen sharing. Yep, thank you.
Sorry, I didn't unmute myself. So Ute, can you see my screen?
Yes.
Good, thank you. So you should notice now that we've kind of been zooming in through the talks. Ute gave an introduction to the applications of machine learning in the solar system. Hannah looked at the application of machine learning to ICMEs, and then Martin described what you can do once you have those CMEs. So now I'm going to go on to describe the application of machine learning to what then happens at Earth. So specifically the topic of geomagnetically induced currents, those are GICs. And the question I wanted to answer in this study is, can we produce a useful forecast of GICs and power grids from solar wind data? This is a regional study for Austria. So it is not a global result. I think that's interesting to keep in mind while we go through this. So GICs are a modern day phenomenon. They've only existed for as long as we've had a grounded infrastructure on the Earth's surface. That includes telegraph lines and power grids. The most well-known event to have affected the power grid was in 1989. This occurred in Quebec. It was the result of a very powerful geomagnetic storm that caused a transformer to overheat in the Quebec power grid. That caused the tripping of further transformers down the line, and within 1 minute of that transformer overheating, there was a power outage in a whole region, including the city of Quebec. And 10 hours later, they were still restoring power. It was a very cold night. It was absolutely not ideal. So now the question is, how do we end up getting effects in the power grid from space weather? I should also briefly say what I do, because I am a geomagnetist. I work with measurements of the geomagnetic field. Those were done at the Conrad Observatory, which belongs to the ZAMG. And we take those geomagnetic variations and we look at then how those are caused by space weather. The interactions of particularly ICMEs with the geomagnetic field cause rapid magnetic variations, which through an induction effect induce geoelectric fields in the ground. This ends up as an EMF that flows through the loop formed by the power grid lines and the ground. They flow through the transformers, which is where the problem lies, because transformers are not built to handle currents that are not AC flowing through them. They are built for AC, and the GICs that flow from the Earth to the power grid are primarily DC because they are so slowly varying. So when you get DC in transformers, they can cause a variety of problems, the worst being overheating. So in the mild case, you can just get some mild operation problems in the transformers and in the power grid. But if you get prolonged large DC, you get an overheating of the transformer and eventual burnout or explosion if it's really bad. So the picture on the right shows the transformer windings after a fire. That is the one in Quebec. That is what led to that power outage that I showed in the beginning. So unsurprisingly, there are quite a few people who are interested in GIC forecasts, those primarily being the power grid operators, because there are mitigation strategies that they can apply to reduce the potentially negative effects of GICs. The Austrian power grid is interested in this. We are in contact with them, and we have built up a good relationship with them over the years. That's sort of the background to this project. But the problem of forecasting GICs is that in the past, basically all studies have concentrated on forecasting the geomagnetic variations, which I would just call DBDT. The problem here is that the geoelectric field that results from those is dependent on the frequency of dBdt. So in order to get an accurate geoelectric field forecast, which is what then directly leads into the GICs, you need a very good estimate of the frequency content of dBdt. And in forecasting dBdt alone, you don't get a very good estimate of the geoelectric field. And so in this study, I was interested in looking instead at forecasting the geoelectric field rather than dBdt. And if you're wondering why in Austria, we are in a unique position because we've had actual measurements of GICs since 2016. The studies into GICs have been running since 2014, and the long-term measurements are since 2016. So we have now 6 years of data from multiple stations. The arrows are number 1 and number 5. These are 2 stations with larger scales of GICs, which are more interesting because the larger the GICs, the potentially more damaging they can be. And so I'm going to look at how well we can forecast the GICs in these 2 stations from solar wind data. Now there's a question before you can get into that, and exactly what do we want to forecast? Because the geoelectric field, we can model that and take it directly into GIC. If you know the GICs at one station, you can find a linear combination of the northward and the eastward geoelectric field components to calculate the currents. But we have no measurements of the geoelectric field. The only confirmation we have that our geoelectric field modeling is good is because we can compare it to GIC measurements and we see there's very good agreement. So we know we're doing a good job, but that's still a downside to that. On the other hand, we could train the model on the GIC station data that we have measured, because this is the actual ground truth, which would be ideal to try and forecast. But we don't have many events with large scales, which is the most interesting thing. And the data is very noisy. And there's often a cap on the maximum value because the GICs that we measure keep exceeding the maximum GIC value that the power grid operators were expecting. And so they have to keep upping the cap in their instruments. So in the end, I decided to just look at both and compare them. And the tool I used is a long short-term memory network, which is a type of recurrent neural network. This is useful for time series forecasting because it has a sort of internal memory where it can look at past data to make a forecast of the next data, which makes them a good tool for this kind of study. The input to the LSTM then is the past 2 hours of solar wind data that was measured at L1. It being measured at L1 gives us an advanced lead time of about 20 to 60 minutes, depending on the solar wind speed. And that's then used to predict the maximum level of GICs in the 40 minutes following measurements, or in the 30 minutes actually. So what that looks like once it's built up is this. The input goes in here. This is the solar wind data. That includes the speed, the density, and the magnetic field, the interplanetary magnetic field. This goes through one more LSTM layer and then is split into 2, where it's trained on 2 different targets. So in each of those, it goes through an attention layer, which is a neural net that is made to mimic human attention, in that it takes what it sees as interesting and it discards the information that it finds as not useful. One side of the LSTM outputs the magnitude of the geoelectric field, because this is an easier task than the other side. This it can do to some good level. The second task, which was more an auxiliary task, or a secondary one, was to output the direction of the geoelectric field. Because as I showed in the formula before for calculating the GICs, you need to, the direction of the field is also important to calculating the scales of GICs. It's not just a linear combination of the 2 components of the geoelectric field. The data set was a full 26 years of data of geomagnetic field measurements, which was split into 21 years for training and 5 years for testing. And so then what we get out is we have 2 models. This one is the GIC calculated from LSTMs trained to output the geoelectric field. So that's in the end 2, because it outputs EX and DY, the northward and the eastward components. And then we also trained the model on the observed GICs, and then to see which one works better. And in the end, it's actually kind of a toss-up between the two of them. Because if you take the data from the LSTM trained to output the geoelectric field, the problem is that those actually produce one direction of the geoelectric field better, namely the northward component. The eastward component is not predicted as well. So the power grid station with the GICs that depend strongly on the northward component is predicted better than the other one, which depends strongly on the eastward component. And this is a result that's also been found in some similar studies that have been done on the geoelectric field, probably because that direction of field variation depends more strongly on regional currents and not as strongly on the solar wind interaction. So there is not really a definitive outcome in this on which method is better. They're roughly similar, but in any case, they can forecast the GICs in the station to some degree. And here's a time series showing how it would have looked if it had been running during the September 2017 geomagnetic storm. And what you see, so in colored lines are the GIC measurements that we have from the stations in Austria. The black lines are the two different models. And what you see is that it is good at predicting when there's going to be an active period, but it is not good at matching the scales. So if you're going to take this as to say, okay, there's something coming and we don't know exactly how big it'll be, then this is useful. But to improve it, you would need to combine it with more information on the magnetosphere and the current state of the current systems in the ionosphere and elsewhere to improve the predictions. And in that regard, we've answered how well can we predict it? It's a useful baseline. And it was a useful study because there so far have not been many other places with GIC measurements that could conduct this kind of study. And that was the important output. And where it'll be interesting to go with this is to incorporate it with other models such as PredStorm, where we have forecasts of the incoming solar wind. And so you can get forecasts of the GICs for a few days. And you can see the full study here under this link and the code that was used to develop all the machine learning models and produce the plots is here. And with that, I'm done.
Thank you, Rachel. And thanks again to all of the speakers. So to Hannah, Martin, and yeah, Rachel again.